Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 5D. I'm Pranjal Banage, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, ICICT 2026 in London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you'll enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for questions and answers. In 10 minutes, I'll raise a gentle reminder. There's another request to all the participants that you all stay connected with us till the closing remarks. If you have any queries or updates, then you can write it to me or to my co host in the chat box. Just before we start the session, I would like to introduce you all to the session chair of this session, Dr. Evzel Abdul Qadir. He is a senior lecturer at Universitas Islam Riau, Indonesia, a senior member of IEEE and a member of ACM. His research interests include software quality, models and architectures, software measurements, information systems, software engineering, machine learning, information and cybersecurity, and e-systems. I would like to invite him to kindly deliver the opening remarks. Dr. Evzel. Moving forward, we'll move to the next session chair, which is Professor Narendra Londe. He is presently working as a professor in the Department of Electrical Engineering of National Institute of Technology, Raipur, India. He has 15 years of rich experience in academics and research. His main areas of research include medical signal and image processing, biomedical instrumentation, speech signal processing, biometrics, intelligent healthcare, brain computer interface, artificial intelligence, and pattern recognition. I would like to invite him to deliver the opening remarks.
Oh, thank you, Pranjal.
Yes.
Very good morning, good afternoon, good evening to all the participants for this session. And as Pranjal has said about this particular session, I would just say that participants should limit their presentations as per the given time. And looking forward for a good session from all the participants. I think Pranjal, you can begin with the session.
Okay, sir. I would now like to start with the papers. I would like to invite Marco Matis to present his paper on a context-aware Moodle AI assistant, design and early student feedback. You may share your screen and start with your presentation.
Thank you very much. Just a second. Okay, so just can you see my screen? Is everything okay?
Yes, it's visible.
Yeah. So hi everyone. Today I'm going to present you a paper titled Context Moodle AI Assistant Design and Early Student Feedback. So artificial intelligence is increasingly being actually integrated into higher education, particularly within learning management systems. So many institutions actually are experimenting with AI assistants to provide faster responses, automated support, and more personalized learning experiences. But however, in a formal university context, reliability, and contextual accuracy remain critical concerns. So AI tools, for example, must align with official course regulations and, for example, institutional policies. So in this paper, we introduce AVA, context-aware AI assistant embedded directly within Moodle, designed to provide accurate course-specific procedural support grounded in official rules and individual student data. So the problem, actually, despite the growing adoption of AI tools in education, there is still a clear gap between general purpose chatbots and the specific needs of structured university courses. So in large classes, students frequently ask questions about grading, thresholds, pass conditions, reliability for reassessments, and other, for example, procedural matters. So these queries are often repetitive and, for example, create additional administrative workload for instructors. Also, at the same time, a lot of generic AI chatbots do not have access to official course regulations or individual rate data. And as a result, their responses may be overly general or contextually inaccurate or, for example, misaligned with institutional rules. So this actually highlights the need for the controlled domain-specific AI solution embedded directly within institutional learning management environment. So this study actually, or the primary aim of this study was to design and implement a context-aware AI assistant fully actually integrated within Moodle learning management system. Actually, a key design principle was strict constraint. The assistant was intentionally limited to official course rules and to official course and the individual grade data. So it does not access external sources and does not provide general academic tutoring, just official course rules and individual grade data. In addition to presenting the systems, in addition to presenting the system architecture, we actually conducted a pilot evaluation to examine students' perception of usefulness, information quality, and actually trust. So importantly, this study focuses on feasibility and early acceptance in an authentic course settings rather than on, for example, measuring learning outcomes. So what's actually AVA? It's shortened from Artificial Intelligence Virtual Assistant. AVA is actually Moodle integrated AI assistant implemented as a block plugin within the learning management system environment. We are using LMS Moodle, so we actually integrated our virtual assistant into this LMS. It's actually powered by the OpenAI API, and its operation is strictly constrained by institutional data, as I mentioned earlier. For example, unlike general purpose chatbots, AVA is embedded directly within the Moodle LMS, which allows it to access official course rules, individual student grades records in real time. Actually, its purpose is not tutoring or open-ended academic discussion. Instead, it focuses only on procedural and administrative support, such as, for example, clarifying grading thresholds, pass conditions, etc. As you can see on this picture, here is actually presented the architecture of the AVA system. In terms of workflow, instructors first need to define all official course regulations within the system. So this structured content serves as a source of truth. And when students when the student asks a question, the system retrieves their individual grades from Moodle and dynamically inserts this data into predefined placeholders to actually communicate with Open AI API. The AI then generates a personalized response grounded exclusively in course rules and institutional data. So this ensures contextual accuracy, reliability, and alignment with official policies. We actually implemented AVA in a second semester undergraduate course delivered in a blended learning format. So the course actually included 144 enrolled students, and 66 of them actively used the assistant and were included in the final evaluation. The course structure was particularly suitable for this pilot implementation, as it actually continued multiple grading thresholds, procedural conditions, and etc. Students were actually required to meet various score criteria in order to pass the course, and some activities allowed reassessments under the specific conditions. So the assistant was actually introduced mid-semester and remained available to all the students within the Moodle environment. The evaluation actually combined two sources of the data. First, we analyzed interaction logs to understand how students were actually using the assistant within the course. And second, we conducted an end-of-course survey using a 7-point Likert scale. So only students who had used the assistant at least twice were liable to participate, resulting in 66 valid responses, which is equal to 66 people who have used the assistant more than twice. So the survey which we used measured three main dimensions. It's perceived usefulness, information quality, and privacy concerns. So given the exploratory nature of this actual study, we applied descriptive statistical analysis, focusing on mean values and actually standard deviation rather than inferential statistics or modeling, for example. Let's see our key results in this study. So the results actually indicate a generally positive perception of the assistant. So in terms of perceived usefulness, students reported a high mean score of 6.05. They particularly agreed that the assistant speeds up the access to the course-related information. Then, regarding information quality, the overall mean was 5.77, which means the students perceived the responses as a clear, relevant, and actually complete ones. So especially when clarifying rating thresholds and pass conditions. And interestingly, privacy concerns were very low, with a mean score of 2.0. So most students did not express significant concerns about data misissue or security risks. So overall, the findings suggest that embedding the assistant within the institutional LMS environment contributed to trust and perceived reliability. Limitations and future work of this study So as this was an exploratory pilot study, several limitations must be acknowledged. So first one is that the system was implemented in a single course, which limits generalizability. Second, there was no control or comparison group. So such as, for example, traditional frequently asked question pagers or similar. And third, the study focused on perceived usefulness rather than measuring direct impact on academic performance. So only, and maybe additional, only descriptive statistics analysis were used. For the future research, maybe we will involve deployment across multiple courses and maybe some kind of longitudinal evaluation of usage patterns and the application of inferential models to better understand adoption and acceptance, for example.
Sorry to
And
interrupt,
there's,
Marco, but I would request you to conclude your presentation.
yeah,
Is up.
okay, so in conclusion, this study actually demonstrates the feasibility of context-aware AI assistant embedded directly within learning management system, and students perceived the assessment as highly useful and reported positive evaluations of information quality, while privacy concerns actually remained low. So thank you very much for your attention.
Thank you so much, Marco. It was very insightful to listen to you. The session chair, do you have any questions for him? Sir?
Thank you, Marco. That was nice. AI assistance in a student feedback system is really, and it's a ongoing topic. People are a lot of working on that things. Uh,
Yeah.
I just wanted to learn, means understand that what have you done any work on this particular system, because I could not see any results related to, or how the AI assistance is helping you in designing that feedback system. So have you implemented this, and what are your observations about it?
So we actually designed this assistant as a tool for example, better regulate the course rules, and we can see from the system, for example, the logs and the student questions, so we maybe can analyze them in term of in adapting our course or our knowledge. So if I point it in a good way.
Okay, that's okay. Next presentation, Pranjal.
Okay, yes. Thank you,
Thank
Marco,
you.
for your well-presented talk.
Thank you very much.
Yes. Mm,
Okay.
Moving forward with the next participant, I would like to invite Usasumwen Imaritbe to present his paper on boundary refined 3D unit, refined 3D brain, MRI segmentation with multi-scale attention for schizophrenia analysis. You may present your screen and start with your presentation.
Thank you very much. Just gonna present my screen now. All right, can you see my presentation?
Yes, it's visible. You may move
Okay, all
forward.
right. Thank you very much. Hello everyone. My name is Isasu Mariagbe, and this work we did with John Zhang, titled Borough Attention Net. It's a boundary refined TVD brain MRI segmentation with multi-scale attention for schizophrenia analysis. The work was sponsored by a few funding bodies and taken out at the University of Lethbridge out in Alberta, Canada. I'll start first of all by saying that introducing the topic and challenges. Medical image segmentation, particularly in 3D MRIs, play a foundational role in neuroimaging analysis. Accurate delineation of those anatomical structures directly affects volumetric studies. It also affects connectivity analysis and downstream clinical interpretation. Now, however, many subcortical regions, such as the hippocampus and the amygdala, present subtle tissue transitions and ambiguous boundaries. Even small contour errors can distort morphometric measurements. So while architectures like the UNet and the 3D unit have demonstrated strong volumetric performance, standard loss functions such as the dash and the cross entropy primarily optimize voxel level overlap. They do not explicitly enforce that boundary precision. The gap between volumetric accuracy and boundary accuracy motivates our work. We introduced BOF attention nets, a boundary-refined 3D segmentation model that explicitly models anatomical transactions through multi-scale. For the related works, first of all, the UNet architecture and its volumetric extension, which is a 3D unit, remain the backbone of biomedical image segmentation. Their encoder-decoder design and their skip connections enable effective multi-scale feature extractions. More recently, transformer-enhanced architectures and hybrid CNN attention models have improved contextual understanding. However, even those models often struggle with accurately delineating subtle anatomical boundaries. And from an optimization perspective, most segmentation models rely on dice or cross-entropy laws. Now, while these are effective for volumetric overlap, they do not explicitly constrain contour precision. Boundary-aware losses, such as the boundary laws that was proposed by Kevedek and the related weighted dice formulations, attempt to address this issue by penalizing contour errors. But many of these methods operate only at the loss level. They do not explicitly model boundary transitions within the future learning process. This is where our approach differs. We integrate boundary modeling directly into the decoder through multi-scale boundary attention models. Our approach builds upon the strong volumetric representations of the TVD unit, but will focus specifically on improving the boundary precisions. So rather than modifying the encoder, we target the decoder pathway. At each decoder stage, we introduce a boundary attention model. So instead of blindly concatenating encoder and decoder features, we generate a boundary activation map. Now, this boundary activation map acts as a gating mechanism. It emphasizes transition zones between anatomic structures and suppresses those homogeneous regions that do not contribute to the boundary refinement. So in contrast, purely boundary-aware losses, in contrast to those, we embed boundary modeling directly into the future learning process. Look at the architecture of our BOF attention net. We concatenate the feature maps along the channel dimensions. Our 3x3 convolution helps capture the local spatial context in 3D. Next, our 1x1 convolution compresses the features and focuses on essential boundary cues. Then sigma activation squashes those outputs within a range of 0 and 1 to become our boundary activation map. So once we have our boundary activation map, we apply it to the features with the header map. The effect is that voxels near the anatomic transactions receive higher emphasis, while homogeneous interior regions are suppressed. So this selective emphasis yields sharper segmentation contours. For the encoder of our architecture, now our encoder works in 4 stages, progressively downsampling the input and increasing the number of feature channels. Initially, our input at the encoder is X. Then as it goes down, it applies a 3D max pull to the output of the previous layer for the purpose of halving the spatial resolution. It then applies a block of 2 down 3x3 convolutions, each time followed by a group normalization and a relativation. So this would increase our channels from 1 at stage 1 to 256 at stage 4. Here we have the deepest representation that captures large-scale context. We also have skip connections at each of these stages. These skip connections save the feature maps and pass them directly to the corresponding encoder stage. They allow the decoder to combine fine-grained details from earlier layers with the semantic context from deeper layers. At the bottleneck, which is the bottom, we would have gotten the richest, most abstract features. These features are then passed to the decoder along with the skip connections, where our boundary attention models are waiting to sharpen the edges. For the decoder, moving to the decoder's job is to take the deep, low-resolution features from the encoder and gradually upsample them back to the original resolution, thereby producing the segmentation map. So we start at the best encoder feature, which by now would have gotten the richest semantic information, but also have the lowest partial resolution. We pass it through a bottleneck block, which then becomes the starting point for our decoding. From there, each decoder stage follows a three-step process. One, upsampling. In this process, we take the decoder features of the deeper stage and upsample it using a three-by-three convolution. Then we perform a skip connection concatenation. Here, we concatenate the upsample decoder features with a matching encoder feature. We always do this to restore the fine-grained spatial details that might have been lost in the encoder's downsampling process. Then lastly, the concatenated features pass through our boundary attention model, which computes the boundary logics, highlighting the anatomical edges. Now, these boundaries are then used to refine the feature map. This process will repeat until we reach the final decoder stage, where the refined feature passes through a one-by-one convolution to produce the segmentation logics. The final boundary logics at the top of this stage helps to ensure that it's sharp anatomical edges in the segmentation outputs. Let's dissect our boundary attention model. Now, this is a component which will be responsible for refining the segmentation around the anatomical boundaries. So let's say we start with the input feature map. Our first step is an intermediate feature. We do an intermediate feature extraction here. Here we pass our input through a 3x3 convolution to capture the local spatial context, then followed again by a group normalization to stabilize the training and a value activation to introduce non-linearity. We then compute the boundary logics by applying a one-by-one convolution to reduce the channels to 1. So at this point, these logics are raw scores, indicating boundary likelihood, but yet they are not yet normalized. So next, we apply a sigmoid to map these boundary logics into a range of 0 and 1 to produce our boundary activation map. We then gate with Hadamard again, our original features with these boundary activation maps. So this step acts like a max. It will amplify the boundary relevant voxels and suppress the irrelevant background or the interior regions. Finally, the refined feature map, which we'll call X-refine here, together with the boundary logics, is returned upstream for processing in the decoder. Now, we created a boundary aware loss formulation. So while our architecture models the boundaries explicitly through attention gating, optimization also plays a critical role. Dice loss is widely used for segmentation because it improves volumetric overlap, but however, it does not explicitly constrain that contour precision. So to address this, we incorporate a boundary loss term that penalizes misalignments between predicted and the ground truth contours. So our total loss is the weighted combination of the dice loss and the boundary loss. Now the hyperparameters alpha and beta control the trade-off between the regional level accuracy and the boundary sharpness. So this allows us to jointly optimize overlap and contour fidelity. We conducted some experiments. For the scope of this paper, we didn't talk much about our data preparation and analysis. We conducted some experiments on our data on a set of Kobe retrieved brain MRI scans. We evaluated our model against the standard 3D unit baseline. We used the dice, we used the Hausdorff distance, and we used the average surface distance. And as expected, the dice improved modestly when we introduced our boundary modeling. However, the most significant improvement appears in the Hausdorff distance. It decreased from 4.57 millimeters to 3.08 millimeters when we combine the boundary attention with our boundary aware loss. Now, this reduction in HD was important to us because Hausdorff distance measures the worst case boundary deviation. Now, similarly, our ASD, the average surface distance, improved from 0.18 millimeters to 0.16 millimeters. That was indicative of smoother and more precise contour alignment. So these results confirm that boundary modeling primarily enhances contour precision rather than just simply increasing volumetric overlap. Thank you for your time.
Thank you. Sir, do you have any questions for him?
Yes, it's some really good work.
Thank you.
What I see, Mr. Osus, that what dice score that you have received. Can you show me that table, please, again?
Yeah.
Yes, that you have considered C only and then C plus boundary, then C only and then C plus boundary, and you have received the dice score here 94, 95, and that's
So
that's really a
we had
good outcomes. I truly impressed. But the thing is that how do you decide that multi-scale attention in this particular bonnet? When we talk about multi-scale attention, there is requirement of the strategy that how that multi-scale is going to be applied with the attention. So
yes,
can you please
good
brief
question.
about this and how that has affected your segmentation results?
Good question. Thank you very much. First of all, initially, from our model configuration and our training configuration, we chose to try to test on just cross entropy loss alone, and then we chose to also test with cross entropy loss with our introduced boundary-aware formulations, right? Multi-scale attention here is because we're working on brain MRI images, and we're trying to isolate just a particular the brain for clinicians have lots of tissues, lot of tissues in the brain, a lot of regions. We're trying to isolate just 6 regions that we're focused on for our further analysis, which was the hippocampus, the ventricles, the amygdala, the basal ganglia, the thalamus, and every other region we chose to be the background, right? Multiple attention here was that each time the model is passed through, it's invariantly checking every region that we're training it on, the 6 regions that I've mentioned. And like I said, because of the way the brain is a 3D, the brain MRI is a 3D formulation, right? We needed a multiple attention that's able to isolate the pixels and the voxels rather in 3 dimension, right? And that's why we try to introduce our boundary aware loss formulation as well, because some tissues, some regions overlap on each other.
Right. That's very good. Thank you so much, Pranjal.
Yes, sir.
What about Professor Kadir? Is he has he joined?
I think he just joined, sir.
Yes, I am here.
Okay, sir.
Yes.
If you have any questions, sir, please.
I just joined. Just go ahead.
Okay.
Go ahead. Yeah, okay.
Okay. Thank you so much, Osasum Wen, for your informative and engaging presentation.
Thanks for your time.
Thank you.
Mhm.
Now that our session chair is here, I would like to introduce him.
Yes,
Dr.
thank you. Thank you. Yeah.
Dr. Evzil Abdul Qadir. He is a senior lecturer at Universitas Islam Riau, Indonesia, a senior member of IEEE, and a member of ACM. His research interests include software quality, models and architectures, software measurements, information systems, software engineering, machine learning, information and cybersecurity, and e-systems. Sir, would you like to deliver some opening remarks?
Yes, yes, thank you, Pranjal. Yes. Thank you so much for the committee inviting me as a session chair in this US. And I hope this session running well, and thank you so much.
Thank you so much, sir. Moving forward, I would like to call upon Jose Baculima Suarez to present his paper on deep learning for brain tumor segmentation, an architectural review from CNN unit to transformers using ECRTM-driven knowledge synthesis. You may present your screen and proceed with your presentation. Mr. Jose?
Hi, everybody. Let me share the screen.
Yes, yes, sure.
Can you see?
Yes, sir, it's visible.
Okay. Okay, good morning. My name is Jose Paculima Suarez, and I'm presenting our paper titled Deep Learning for Brain Tumor Segmentation and Architectural Review from CNN Unit to Transformers using ECRTM Driving Knowledge System Synthesis. This is a joint with work with Universidad Católica de Cuenca y Universidad Politécnica Salesiana en Ecuador. Introduction. Why automate the brain tumor segmentation? Automate brain tumor segmentation from medical imaging is a cornerstone of modern neuro-oncology, providing critical support for clinical diagnosis, treatment planning, and longitudinal monitoring of disease progressions. Accurate segmentation delineates tumor boundaries, quantifies tumor volume, and characterizes subregiones. All essential for precise surgical resection, target radiation therapy, and evaluating chemotherapeutic efficacy. While manual segmentation remains the clinical standard, it is time-consuming and subject to variability, reinforcing the need for automate deep learning solutions validate of very much such as the Bratz challenge. Traditional CNNs, particularly the UNet architecture, have significantly advanced this field. However, the inherent limitation lies in localized receptive files, which often prove insufficient for accurately segmenting tumors, exhibiting a significant variability in size and shape, and which impede the robust capture of global spatial correlation crucial for delineating irregularity shaped or small lesions. Methodology, data collection and system filtering. Our data collection followed for a three-stage. First, exploratory analysis and initial query was conducted in ScienceDirect focusing on the 1993 and 1996 period, retrieving 236 articles. This preliminary analysis confirmed that the file is rapidly migrating from purely convolutional architectures toward transformers and state space models. Second, a multi-source extraction, a target search was executed across Scopus, Web of Science, and ScienceDirect using Boolean operation, yielding 198 initial records. Third, quality filtering duplicate and out of scope articles, those without a deep learning focus. They were removed, resulting a final corpus of 138 articles, 99 from Web of Science, 93 for 23, sorry, for ScienceDirect, and 16 for Scopus. Part of the methodology, we do a deep semantic modeling with ECRTM, given the technical nature of the corpus, the embedding coherence regularized topic model, ECRTM, was implemented. Unlike traditional models like LDM, LDA, that assume direct-led distributions, this model, ECRTM, utilizes a variation autoencoder architecture combined with semantic regulation based on the embedding space. The model has two components, an inference encoder, a dense neural network that takes the back of words, a representation of each document section and project it into a low-dimensional latent topic space. And a generation decoder which reconstructs the original document from the learning topic distribution data using a topic term matrix beta. To maximize coherence, ECRMTM employs an optimal transport loss between topic embeddings and works embeddings from fast tests, ensuring that grouped terms not only statistically occur, but possess actual semantic proximity. Show the training parameters and the full loss function. Fundamentals, MRI modalities and evaluation metrics. Brain tumor segmentation is typical performed or multimodal MRI data. T1 weighted, T1 with contrast enhanced, T1 GD or T1C. T2 weighted and flyer sequences, each highlighting different tissues characteristics. Accurate segmentation requires delineation of three subregions, the enhancing tumor, the necrotic core, and the peritumoral edema. Performance is evaluated using three standard metrics, the disease similarity coefficients, the Hausdorff distance, and the insertion over unit. It is applied to whole tumor, tumor core, and enhancing tumor. The UNET paradigm and convolution constraints. The UNET architecture revolutionized biomedical segmentation through its symmetric encoder-decoder structure and skip connection. This design facilitates the fusion of high-resolution spatial features from the constraining path with semantical dense information from the expansive path, enabling simultaneous contextual understanding and precise location. Skip connection are pivotal. They concatenate feature maps across the bottleneck to mitigate information loss during pooling and restore spatial integrity, which is critical for delineating integrate anatomical structures. Architectural variants such as UNET, UNET++, multi-res UNET, and UNET++, introduce nested connection and residual paths to optimize gradient flow and feature functions. The 3D UNET and BNet adapted this operation for volumetric computational tomographics and MRI data. Despite this success, standard UNETs are constrained by the local receptive files and convolutional kernels, which limit the capacity to model global semantic context and long-range dependencies. While these interactions improve convolution efficiency, they frequently lack a native mechanism for capturing comprehensible global information, a limitation that persists across poorly CNN-based frameworks. The receptive files optimization via attention mechanism. To overcome local constraints, attention mechanisms have been integrated to a dynamically wake feature importance across expansive spatial extents. In medical imaging, these are categorized into channel-wise attention, which recalibrates feature response by modeling interdependencies, and spatial attention, which prioritizes informative regions such as tumor boundaries. Hybrid models leverage both dimensions to produce robust representation while filtering irrelevant background noise. A significant innovation is the implementation of attention gates within skip connection. Attention gates refine information propagation by highlighting irrelevant activation from the encoder before merging them with the decoder's upsampling features. The selective emphasis enhances generation and reduces the computational cost of processing non-informative voxels, resulting in superior segmentation accuracy across heterogeneous tissue types. The shift towards transformers and hybrid architectures. The integration of transformer addresses the inherent inability of CNNs to capture long-range dependencies by employing a self-attention for global context modeling. By treating image patch sequences, adapting this vision transforming paradigms, these models establish a global perspective essential to identify diffuse boundaries in complex brain. MRI, a current state-of-the-art design for favor hybrid frameworks, such as TransUnet or TransMet, which synergy CNN-based local features extraction with transformer-based global modeling. Volumetric precision and efficiency have been further optimized through the swim transformers, which utilize shifted windows to capture in hierarchical features with reduced computational complexity. Models like SwingUnet and UNet Air utilize these blocks to process 3D scans across multiple resolution, connecting transformers encoders directly to decoders via skip connections. This coverage this convergence of paradigms provides the necessary balance between fine-grained detail and broad semantic context for effective diagnostic treatment planning. Trends from hybrid transforming to state space model. Recent innovations have pivoted toward optimizing transformer architectures to address high computational costs and scarcity inherent in medical imaging. Deformable transforms allow attention modules to focus dynamically on most relevant features, significantly enhancing segmentation performance while maintaining efficiency. The nested modality aware transform utilize modality attention and establish correlation between different MRI sequences, improving overall quality tumor delineation by liberating complementary information across modalities.
Hello.
Eh,
Excuse me, Jose. I'm so sorry to interrupt, but your time is up. You'll have to conclude your presentation.
Okay, so okay, by conclusions, the architectural landscape of brain tumor segmentation is undergoing a transformative shift, transforming from the localized feature extraction of convolutional network toward the global context assimilation of transformers and high-efficiency state space models. This research synthesizes evidence from the final corpus. The findings confirm that while CNN-based units establish vital foundation, their receptive files limitation are being systematic overcome by self-attention mechanisms and hybrid designs like TransUnet and SwingUnet. Essential for navigate for the morphological heterogeneity and diffuse boundaries characteristics of gliomas. Beyond either architectures, the analysis reveals an emergency efficiency for frontiers driven by state space models, specifically Mamba architectures which offer linear complexity with respect to sequential length, bypassing the quadratic bundle of traditional transformers. Looking forward, the purpose of personalized medicine in neuro-oncology necessitates the refinement of architectures that balance this computational efficiency with diagnostical precision. Thank you.
The session chair, so do you have any questions for him?
Yes, I have one question. Okay, thank you, Jose, for the presentation. How many data that you collected, and from where the data you get it? Is it from hospitals or governments or others? Can you hear me? Yeah.
Yes.
Yeah.
This is a brief review about a literature review about deep learning for brain tumor segmentation previous to a project, research project to when we recopilate data of hospitals. the principal problem of the recollection of data is that the data is not structured, and the bioethic process that we need to process this data. But is we have a project to analyze with these novel architectures for brain tumor segmentation.
Yeah, okay. As I know, normally as hospital data or medical data is very privacy. Then hospital very hard to get to the researchers. It's okay. The concern is now when you are doing on the deep learning. I see your title is deep learning for brain tumor segmentation. So the net accurate data with the variety get from many hospital, 3 or 4 hospital, and others the Parisi and the Pulumas. Okay, thank you, Jess, for the presentation.
Thank you.
Yeah, all right.
Thank you so much, Jose, for that impactful presentation. Next, I would like to call upon Surasak Petmane to present his paper on digital government through formal verification and cloud infrastructure. You may present your screen and proceed with your presentation.
Thank you. I will present my screen. Yes. Okay. Okay, let me see. Okay, thank you very much for attend my talk. Today, I think I will talk quite for a speed talk. I think the first I will present my research work about digital government through formal verification of cloud infrastructure. For the program, you can read the paper, and in the paper contain about the link that you can download for the program that you can install and enjoy yourself. Back to the presentation. I think for the digital government and cloud, for now, government try to work on private cloud like we host it, and this is the mission critical because it will impact about the citizen or the user like us. And for the just empirical monitoring useful. However, they are not guarantee about behavior in uncertainty situation. So we want to provide quantitative assurance for reliability, availability, and cost using formal verification. So we need about availability. For example, the service reachable when needed, and reliability remain the operation over time risk and recovering costs. For the contribution for the model, I model the cloud, private cloud in formal model like MDP, and we will know later this slide what MDP is. And we specify property like the requirement in PCTL, one the language for formal language like formal verification, and using Prism that is the tool for formal model checking. And we asset the scenario-based evaluation and then provide the result to support decision of the policy. This is my methodology. First, we capture the behavior of the cloud into the model, as we call earlier MDP. It stands for Markov decision process, and we specify requirement in PCTL. This stands for probabilistic computation tree logic, and use Prism to compute probability and expected reward. the cost. And we compare the scenario, three scenario. This is the MDP. For the MDP, we analysis about the state. This is the state, and this is the start state. And then this is the action. For example, allocate, recovery, or reconfiguration, and so on. This is the probability, transition probability. For example, failure, repair, or degradation. This is the atomic proposition, like the Luma of the uh, activity, and this is the Rabel. And we model three modules. First, compute, storage, network, and then management. This is the property specification. This property capture from requirement. For example, availability. In this property, eventually operational. For example, uh, this cloud computing can available eventually like this. Or another property, this is reliability over horizon time. G mean always. It mean what minimum probability that the cloud always work in operational in T period. And this is the failure risk. What max probability that eventually fail. And this is the expected recovery cost, the cost that we use when we operate them. The model parameter, I add the model parameter, and if you see in the paper, it's contained in the table 1. For example, failure rate, repair rate, and resource utilization, and recovery cost. For the number of the value that we assign, actually we have another work that published earlier, and then we move to this paper, and then we use the parameter from that. The experiment scenario, we divide into 3 scenarios. The first, the baseline, no automated recovery or tuning. And the second scenario, verify open source like Eucalyptus. We try to enhance automation, and we try to replication. For example, we set the rate for the failure rate and recovery rate like this. And for the third one, we verify the commercial cloud, for example, vCloud, and we try to add all integration and then proactive handling. And this is the result. You can see that in baseline, the availability probability like this, and the expected cost like the one baseline. And for the open source, the availability is is better than the baseline, and for commercial as well better than all of them. And you can see the expectation uh, recovery cost will be nice for open source, that we try to capture the policy, or we try to automate one. And especially for the commercial one, if we try to orchestra like that, the recovery cost will reduce. Uh, as we use the formal verification, we support auditability, and we can trust, and we can guarantee the policy help the decision maker to assign the policy or policy maker like that. And then for the conclusion, this is the contribution. We try to model cloud computing in the term of formal verification, and then we verify them, and the result will be the support of the policy. And for the future work, I think I will add the continuous verification and try to handle about the scalability, because for now we stuck with the scalability. For example, the state space too large like that. And thank you very much for listening my presentation. Any questions?
Yes, Surasa, thank you for presentation. So, is it digital government? Is it deployed uh, uh, till now or just doing research? And how about the privacy? Because the cloud concern, one of the concern is security. Sorry, I mean security. Because
Yeah.
uh, one of the concern in the cloud is many people attack to getting data to the cloud. Yeah.
Yeah, thank you for the question. Nice,
Yeah.
nice. We are the first we already deploy in our organization,
Okay.
and we already concerned about the security as well, and that's why we select private cloud for the experiment. And for my previous work, I try to implement the static one without formal verification. And then from now we move to formal verification to handle the things like policy, including
Okay, thank you.
Thank you so much, Surasak. I appreciate your time and effort to deliver such an excellent presentation.
thanks you.
Now,